All right, so now we're going to talk about bonding. This is sort of the basis of a molecular structure, is that atoms are bound together. Again, because this is organic chemistry, we're paying attention to that row 2 and carbon in particular. These are going to be covalent bonds that we're talking about. Covalent bonds, the one thing that I want you to have in mind when you hear covalent is sharing. Right? Those should be sort of synonymous in your mind, because that's what a covalent bond is when electrons are being shared between atoms, okay? So here is a good example. Here we have a single bond between two chlorine atoms. So chlorine gas is two chlorine atoms with a single bond. You could say that there's a sharing of 2 electrons here. Notice that, well, so a single bond is the sharing of 2 electrons. Here we have a double bond, and the double bond is a sharing of 4 electrons, whereas a triple bond is going to be the sharing of 6 electrons, okay? And so this is just an example of those electrons being shared. Again, that's what I want you to think of, covalent sharing of electrons. Okay, so then let's talk about what happens when two atoms come together and form a covalent bond. This graph is something that you're going to see a lot, and you just sort of really want to understand what it's saying here. So first of all, if we look on the y-axis is energy, and on the x-axis is internuclear distance. That means the distance between 2 hydrogen atoms. And so that's what this graph is representing, is we're going to take 2 hydrogen atoms from very far away, all the way out here where their energy is 0. And then we're going to start to bring them closer together. And what happens is, as they approach this sort of ideal distance, the energy begins to drop. Okay. And then all of a sudden they get to this ideal distance. This is the bond length for this covalent bond. The energy starts to shoot up rapidly. That's if you took a hydrogen molecule and you tried to smush it together too closely, those nuclei would begin to repel each other. But you see, the real key point is this right here, that there's this minimum distance that's actually lower in energy than when those 2 hydrogen atoms are all by themselves, right? So that's this covalent bond being formed. If I took 2 hydrogen atoms and brought them together, they would form a covalent bond, and it would have this sort of ideal distance right here of 0.74 angstroms. So this is just an important, I think this graph is something that you see all the time, and if you don't understand it, it's just one of those things that you want to have a good understanding of. We'll talk about why bonds form in 1 second. The most important thing that we got to do first is figure out how to count valence electrons, okay? So let's remember what valence electrons are. Those are the highest energy electrons in an atom. We call that like the outer shell. And they are the electrons that participate in covalent bonding, okay? So first thing we got to be able to do is to know how many valence electrons an atom has, and we do that by looking at the periodic table. So it's pretty straightforward. Hydrogen, everybody in this column has 1 valence electron. Everybody in this column has 2 in this second column with beryllium. Boron has 3 valence electrons. Carbon has 4, nitrogen 5, oxygen 6, the halogen 7, and the noble gases have 8, with actually this exception of helium, which only has 2 electrons because it's really tiny. So this is the way to, it corresponds to the group number. However, we want to be able to do this. One of the things that you want to practice doing is, let's say that I don't have any numbers at the top. I'm just given a blank periodic table. Can I still figure out the number of valence electrons of, say, nitrogen? So then you're going to go, starting from left to right, you're just going to count 1, 2, skip the transition metals, 3, 4, 5 for nitrogen. Okay, so you just want to have that procedure down. If you're given a blank periodic table, do you know how to find the correct number of valence electrons? So why is that important? real question is, why do covalent bonds form in the first place? Why is it lower energy for those two hydrogen atoms to be this certain distance where they're sharing their electrons as opposed to further away? And the reason is because atoms want to have a full valence shell. We call this also an octet, although it can be a misnomer because hydrogen only likes to have two in its octet. But yes, this is what it's a full valence shell. The bottom line is full valences are happy, stable, low energy. That's why the noble gases are so noble. They don't react at all because they are perfectly happy all by themselves with their full valence shells. So again, most atoms, carbon, oxygen, nitrogen, and all the halogens that we'll be dealing with like to have 8 electrons in their valence shell to fill their octet. Hydrogen is going to be an exception. It only has room for 2, okay? And then boron is going to be another exception that has room for 6, okay? So it doesn't need the full 8. And then if we just want to like go back to this other thing that we were looking at here, this picture, we can see what this is showing you here. This one's my red chlorine. This one's my blue chlorine. Chlorine, because of where it is on the periodic table, take a second and see if you can't figure out how many valence electrons it should have. Looking at this. All right, so I already did part of the numbering, 5, 6, 7. All right, so chlorine, right, because chlorine's over here, so it should have 7 valence electrons. So each one of these atoms has, I got 7 reds, 7 blues. And then you can see that they're sharing those electrons in order for both of them to have 8 in that shell. All right. Same thing with the oxygen. Oxygen originally has 6. Nitrogen originally has 5. And so this is what this image is sort of showing, that there is this sharing of electrons that's occurring in order to give everybody that full valence shell. The last thing we want to talk about with bonds is this idea of polar bonds, okay? We talk about how a covalent bond means that electrons are being shared. They're not always being shared equally, okay? Some atoms are electron hogs, some elements rather are electron hogs. They will hoard electron density within the bond, okay? So let's take a look at a non-covalent bond, one where there's equal sharing of electron density. So anytime 2 atoms are the same identity, the same element, they can't push or pull any stronger than one another. So those are going to be non-polar covalent bonds, where this electron density, that's what's pictured here, this bubble, is this electron density is evenly distributed. If we want to take a look at a polar covalent bond, this is going to be where the electron distribution is uneven within that covalent bond. So electrons are still being shared. It's just that they're not being shared evenly. One of these members is hogging it on him or herself. So in this case, chlorine is actually the electron hog. So what's being pictured here is the blue means there's high electron density, and the red means there's low electron density. And we can see that shape as well, right? The chlorine is hogging that electron density onto itself. These symbols here mean partial positive. So we would say that this end of this bond has a partial positive charge, whereas this end of this bond has a partial negative charge. And we'll also see this represented with arrows called dipole moments that point from areas of low density to areas of high density, okay? The other extreme, not really important for organic chemistry, again, we're going to be focusing on covalent bonds, but nonetheless, just to have it said, right? So the other extreme being an ionic bond, which is a complete transfer of an electron from one element to the other. So they're no longer being shared. Chlorine's completely taken this electron from sodium. So different than the hydrogen and chlorine bond. That's why this one would get a partial positive charge, while this one has a full positive and negative charge, okay? How do we tell how polar a bond is? This is using this concept, this term electronegativity. So here's another vocab word that you're gonna have to know. Electronegativity is how strongly an atom attracts a share of electrons within a bond. So there's this scale that was developed called the Pauling electronegativity scale, where each element is given a certain value. And The difference between two elements, so if I took, for example, a HF bond, that would have a difference of 1.9 in my electronegativity. It's always a positive number. So I would take 4, subtract 2.1, get 1.9, right? Yeah. And then I could see on my scale here, that is an incredibly polar bond, sort of lying almost more towards an ionic bond. Okay, but this is the scale where down here, this is a difference of electronegativity of 0. That would be non-polar. And then the larger the difference in electronegativity, the more polar that bond gets, right? And again, polar is an unequal distribution of electrons, partial charges, you should think. Okay, so yeah, so that, anyways, it's sort of a sliding scale. This value is this kind of like semi-arbitrary value before we say that the bond is actually polar. So for example, one classic non-polar bond would be carbon and hydrogen. There is a slight difference of electronegativity there, but it is just too tiny for the bond to be considered polar. These bonds behave as non-polar bonds. Okay, cool. All right, so let's keep on building towards getting to structures. Crap. It's over here.